Okay, so for part 2 of homework 9-3 here, right? So for part 2, just questions 7 and 8 to wrap up, and I'll go through these pretty quickly. And so for the most part, I'll just kind of show you obviously the answers and the work here. If you do need further explanation, either one, come in and see me so I can give you some help, or two, go back and consult example 6, question 6 from this homework as well, because I gave maybe a more thorough explanation there. So it's not going to be as involved here, but I will still go through this. So anyway, when we have a film like this, when it's air and then film and then back to air, the key is the first reflection is out of phase with the original, the second reflection is in phase with the original. So those two reflections are out of phase with each other, right? Which is why if we want them to constructively interfere, we need to offset them by half of a wavelength. Since they're already out of phase, we need to offset them by half of a wavelength, so they'll be in phase with each other. So 2 times the thickness, right down and back, that's why it's a 2t, equals 1/2 the wavelength, so the thickness equals 1/4 the wavelength. So all I need to do then is find the wavelength in the film. Well, to do that, I use my index of refraction to help me find the velocity in the film, right? So my velocity in the film, just using the index of refraction there. And then since I know the frequency is constant, I have my velocity, I have my frequency. Finding the wavelength in the film is pretty easy. And then finally plugging that back in up here to find the thickness. So 1/4 of the wavelength equals the thickness. So 1.09 meters or 109 nanometers, right? So making sure you're comfortable with film like this. Again, feel free to pause the video if you need to stop and replay this at all if you do. But I'm going to continue to scroll on. So question 8, again, same type of thing, right? This time, however, we've got a piece of glass that is, right, covered with a thin layer of gasoline. Probably not the best film, but whatever, it works. So anyway, we've got gasoline, and then if we look at this again, air has an index of 1, the gasoline has an index of 1.4, and then the glass has an index of 1.5. So since this one is steadily increasing, both reflections are out of phase with the original. Since they're both out of phase with the original, they would be in phase with each other. And therefore, if I want to get a glare, right, if I want to see, in this case they say we want to get a reflection, right, a beam of light shining on a particular film, what is the wavelength of light in film so that we get a bright reflection, then if we want a bright reflection, we want to maintain the fact that they're in phase, so we want to offset them by a full wavelength, right, not half a wavelength because that would put them out of phase, but a full wavelength. So once again, 2t down and back would be offset by a full wavelength, which means t would equal half the wavelength. And then just like we did up above, we need to find our wavelength in the film, right, in the gasoline. So use the index to find the velocity, use the speed of light and the wavelength in air to find the frequency, and then we know that the frequency is constant, so use the frequency and my velocity in the gasoline to find the wavelength, and then plug the wavelength in to find my final answer. So anyway, 2 times 10 to the negative 7th, or 200 nanometers, is how thick this layer of gasoline would need to be in order to get bright constructive interference. So like I said, I don't mean to rush through these too much, but I don't want to waste your time either. So if you do have any further questions on this, come find me so I can give you some help. Otherwise, hopefully you guys are starting to get more and more comfortable with these film and coding type questions. But anyway, that wraps up then homework 9.3 here. So any questions, let me know.